Welcome to Proof by Mathematical Induction, part of the Year 12 Extension 1 course. While this video can be viewed standalone, there are references to content from the advanced course in sequences and series. So if there's anything unfamiliar to you that we mention in these induction videos, feel free to go back and look at some of that. But now let's focus on mathematical induction. And what is it? Well, first of all, we're going to start with a more general question, which is, how do we know a mathematical statement is true for all cases? And how do we prove or disprove a mathematical statement? One way is via deduction, and another way, which is the main focus of these videos, is through induction. But let's start first of all with deduction. Deductive reasoning uses known facts to prove statements, and this is what would be most familiar to you. So let's look at proving the following statement using deductive reasoning. On the left-hand side of this statement, we have a series, and you might recognize it as an arithmetic series because as we progress from one term to the next, we're going up by 4 each time. Now, something that is a little bit different, but you can see that the final term, the nth term, is expressed as 4n plus 1. So let's just double check that this works when we look at the first term, where n equals 1. When n equals 1, we would have 4 lots of 1, which is 4, plus 1, which is 5. So that's good. What about when n equals 2, our second term? When n equals 2, we have 4 lots of 2 is 8, plus 1 is 9. And so you can see that every term does indeed follow this pattern of 4n plus 1. But the overall statement is saying that this series on the left-hand side is actually equal to this expression, n outside of 2n plus 3. So let's use some deductive reasoning to prove this statement is true. What we're going to do is start with the left-hand side, and as we have said, this left-hand side is an arithmetic series. And so in noting that, we can write down some things that we know about arithmetic series. So for this one in particular, the first term, a, is equal to 5, and the common difference is equal to 4. The last term is the nth term, and here it's been given as 4n plus 1. Using this information, we have, I suppose, what is a known fact to us, that the sum of an arithmetic series for n terms is n on 2 outside of a, the first term, plus l, the last term. So let's evaluate the sum of our arithmetic series. The n on 2 out the front remains as an n on 2, and in the brackets we have our first term, a, which is 5, plus our last term, l, which is 4n plus 1. Simplifying what's in the brackets, we get 4n plus 6. And when we drag out a common factor of 2 from within the brackets, we notice that the 2 and the half will cancel out, leaving us simply with n out the front and 2n plus 3 in the brackets. But this is exactly what the right-hand side of the original statement was. So we have shown that the left-hand side is equal to the right-hand side. And we have therefore proved the statement using deductive reasoning because we took a known fact to help us prove the statement. But what about induction or inductive reasoning? Inductive reasoning in maths, or what we call the process of mathematical induction, takes a different approach. Inductive reasoning in mathematics, or the process of mathematical induction, combines generalizations with specific examples to prove a statement. This approach is useful when the only alternative seems to be trial and error, or that is when we have to test specific values. So what we're going to do now is we're going to compare two statements using a trial and error approach. So here's the first statement. Once again, we have a series on the left-hand side, 1/3 plus 1/9 plus 1/27, and so on, all the way up until our nth term, which is 1 on 3 to the power of n. And that is equal to this expression, 3 to the power of n minus 1, all over 2 lots of 3 to the n. And this is true for all n. Our second statement is over here. We have n squared minus n plus 41 is a prime for all values of n. So we're going to look at these two statements side by side, and just note that the value of n that we're talking about is a natural number, that is a counting number. So n can only take on values such as 1, 2, 3, 4, and so on. Okay, so remember we're doing trial and error. So let's start off by trying n equals 1. On the left-hand side, we have 1 over 3 to the power of 1, which is just 1 over 3, or a third. And on the right-hand side, when we substitute n equals 1, we have 3 to the power of 1 minus 1 over 2 lots of 3 to the power of 1. That gives us 2 on the top. The 2 on the top will cancel with the 2 on the denominator, giving us 1/3. So we can see that this statement is true for n equals 1. Let's have a look at our second statement. When we try n equals 1, we get 1 squared minus 1 plus 41. Now, 1 squared is just 1, and so we can see that the 1 and the negative 1 cancel out, leaving us with simply 41. And 41 is a prime number. So we've trialled n equals 1 for both statements, and they've both been good. Let's now try n equals 2. On the left-hand side, we get 1 on 3 to the power of 1 plus 1 on 3 squared. This becomes 1/3 plus 1/9. And when we combine these two fractions together, 1/3 is 3/9, so we get 4/9. The right-hand side, we want to substitute in n equals 2 into this expression. So we have 3 squared minus 1 over 2 lots of 3 squared. 3 squared is 9, and 9 minus 1 gives us 8. And on the bottom we have 2 lots of 9, since 3 squared is 9. And we can see that the 8 over 2 simplifies to give us 4. So we have 4/9. So this statement is true for n equals 2. Let's have a look at our other statement. Subbing in n equals 2, we get 2 squared minus 2 plus 41. And that's equal to 4 minus 2 plus 41, which gives us 43. And 43 is a prime number. Now, you can probably already see how exhausting trial and error can be. We've only trialed n equals 1 and n equals 2. And how much further do we have to go? Do we go from n equals 2 to n equals 3, and then to n equals 4, 5, and so on? Well, yeah, that is kind of what we have to do if we're doing the trial and error approach. But just to make things a little bit quicker, I'm going to let you know that all the way up until 40, things go smoothly. So let's just check n equals 40. Now, in this series on the left-hand side, going from 1/3 and 1/9 and so on, all the way to the 40th term, which is 1 on 3 to the 40, that's going to be a bit of a mission. But luckily I've prepared an Excel spreadsheet. In the first column, we have just the numbers 1 through 40, so they're representing our n values. In the second column, we have the 1 over 3 to the power of n. So 1/3, and then 1/9, and 1 over 27, and so on, but all in decimal form. And then this third column is adding those progressively. So we have 1/3 here, but then this is the sum of both B1 and B2. Sounds like bananas in pajamas. And this next one is the sum from B1 through to B3 and so on. So we can see the sum progressing. Now this column over here, this is the right-hand side formula. And for this particular trial, I'm interested in n equals 40. So when I substitute in 40, I have this expression, 3 to the power of 40 minus 1 over 2 lots of 3 to the 40. Going back to the Excel spreadsheet, and we'll go down to n equals 40, we can see our values here. Now it's actually given us 1/2. So you can see how it just appears to approach 1/2. Now, if you remember your geometric series, this shouldn't actually be surprising to you because we're dealing with a geometric series that has a ratio of less than 1. So this is a convergent series. But regardless, as you look along between the sum of the series, remember this is using the sum, and this formula here, which is the right-hand side formula, this one, all the values are the same. So this Excel spreadsheet is just my way of quickly cheating through the massive computation that you would have to do. So without going any further, when n equals 40, the left-hand side does equal the right-hand side. Time for the second statement. So trialing n equals 40, we get 40 squared minus 40 plus 41. 40 squared is 1600. And when we subtract 40 but then add 41, that's like just adding 1. So we get 1601.